Hello. Today we will be seeing the capacitated vehicle routing problem. This problem looks to find routes to cover all customers where customers have a certain demand, and we need to cover them with the vehicle that has a certain capacity. It's similar to a TSP, but because there's demand and there's capacity on the vehicle, then the vehicle needs to go back to the depot and then start a new route so that it can cover all of the clients. So for example, this problem has 3 routes, which is possible to cover the customers with. There's a formulation where we look to find the minimum cost. We want to cover all of the clients. There's a two-factor elimination constraint, and the capacity of the track can never be surpassed. So let's start. So I'll keep the formulation right here on the left. And in Python, we will be doing first a creation of synthetic data. We're going to create some random data so that we can solve an instance of the problem. And we're going to plot it also. Matplotlib there. I'm gonna fix a seed for the random number so that when you guys try this at home, you can get the same results as I do. So with this, so I'll be using 0 as for the seed for now. So n will be the number of clients. Let's just start with 10 clients. We are going to locate them. I'll have here the x coordinates, and it's going to be random. So we're going to create a random vector of n plus 1 locations. So it's n locations for the clients, and there's 1 extra location for the depot. And I'm going to put this in a 200 by 100 rectangle. So the random numbers here for the y-axis, it's going to go between 0 and 100. And so the first on the 0 position is going to be the depot, and the rest is going to be the clients. So I can plot the depot first, for example. So just the first, the y coordinate, just first. And I'm going to color this red, and I'm going to use a square as marker. There. So that's the depot. I'll also plot the clients. So for the clients, I'm gonna do a slice of the coordinate location. So from the first until the end. And I'm gonna color this blue. So those are all of the clients in the depot right there. All right, so the first thing here, so we have n already. We're looking at the model here. On the left, a set of clients, it goes from 1 till n. So this is going to be a list, n is going to be for I in range 1 till n. So n plus 1. So remember that. So in order to get to n, I need to go one. I need to put one further here because this number here, the range function doesn't take it. Okay. So if we try this, n goes from 1 till 10. Okay. Then we'll have v is gonna be the union of 0. So we can just put together two lists here using the plus operator, just like that. And if we look at it, it's from 0 till 10. Now a, we can write exactly like it is here. So a is going to be the set of arcs. It's going to be I, j for I in v, for j in v, and having f i's different than j. So it's going to be lots of things. So there we go. The cost is going to be, I'm just going to use the Euclidean distance. I'm using a dictionary, so it's going to be, the key for the dictionary is going to be each arc. The value will be the Euclidean distance. I can do that with this function. So it's going to be the difference of the x coordinates. Then the second will be the difference of the y coordinates. And this is going to be for each arc in A. So this looks like this. Now, Q will be the capacity of the vehicle. So I'm just going to set it on 20 for this example. And Q is going to be the demand of each customer, the amount that needs to be delivered for each customer. So it's also going to be a dictionary. So customer I, I'm going to do a random number. So, and this time it's going to be an integer number. So it's going to be an int between 1 and 10. This is going to yield between 1 and 9. The 10 is ignored, is excluded. For I in n, n are the customers. All right. Just notice that if you run this several times, you're going to get different numbers. So I'm going to write it again. So you see how the numbers run, and if this is because the each time the random function is called, then it just generates new numbers. We can always restart everything. So to make sure that you're getting always the same number here, so I'm just going to click here, restart the kernel, and run all of the cells. All right. Okay. So these are actually the numbers that we're going to be using. So for now, I'm going to delete this cell, and now I'm going to start modeling the formulation using Gurobi. So I'm going to assume you guys have the module Gurobi installed in your computers. I'm going to use model, the object model, GRP, and the sum, the quick sum function. That's faster than the sum function that comes with Python, at least to manipulate the objects from Gurobi. All right, so MDL is gonna have the model. It's gonna be CVRP. I'm using a academic license. If you guys are a student at a university, you can get a license for free for the full version of Gurobi at gurobi.com. All right, so the X variable is going to be a dictionary that gets produced like this. So I take the model, I want to add variables, and I'll use the list of args A for indexing, and the variable type is going to be binary. Actually, there's okay. And the other variable, so I have X and U. Now U is going to be MDL add variables also. This so the use only exists for the clients, and the variable type is grb continues. Let's see there. All right. So this is a minimization problem. So model sense is going to be minimize. Keep using some there. And we'll set the objective. So the objective here will be the sum of all of the distances, which are here in the parameter C. So I'll use Gurobi's quick sum function. So it's going to be for each arc, the cost of the arc, for all the arcs in A, and that would be the objective. Now, you can also write ij here instead of just A. You will get the exact same thing, but you will need to change here. So whatever is more convenient for you. Now, the constraints. To add our constraint, I'll just use the function addConst. And this is the sum right there. So it's going to be quick sum of xij's. So the sum is for j's in V having j different than I. All of this for I in N. Let's see, what did I do here wrong? Quick sum xij. All right, okay. So this sum needs to be equal to 1. now it's working. Very similarly, I'm just gonna use this. Copy that. IJs, now the I's from B. So this, I'm gonna make the change even though it doesn't, it will do the same thing. Now here is J. Okay, there. Okay, we can get rid of this by using semicolon there. Okay, so that you don't see the output. Now, for this constraint, the subtotal elimination constraint, we'll use indicator constraints. So it's the same thing at the beginning. Now, first the condition. So whether xij, whenever xij is equal to 1, and we want to enforce that ui plus ui will be uj. And this is for ij's and yarks. But excluding the connections to the depot, so having I different than 0 and j different than 0. I can write it on there so it's easier to see. Okay. Then the last constraints, so I'll have to write this twice. I can write that UI will need to be greater than or equal than QI. This is for I in N. And I'm just gonna copy this. Now it's less than equal, and this would be Q. Okay, good. Now I can run this. Right here I'm running Gurobi 9. And I quickly find the optimal solution. So here we see that the gap is 0. Optimal solution found. And let's plot this solution and see how it looks. So we'll save the active arcs in a list. So it's going to be A, for A in capital A, but I want only those X variables. And so here with the dot X, I'm calling the value of the solution. So I know here we want the X, there are 1. But sometimes for numerical reasons, instead of 1, you're going to get a 0.9999999. And if you compare with 1, it's going to be different. So to avoid any errors there, I always use this comparison. So if it's bigger than 0.9, or you can just put 99, for example, then you're going to get all of the ones. So those are all of the arcs. Let's see how that looks. All right. So if I plot them, it will be easy to see the results. So I'm gonna get the same. I'm gonna use the same code up here. I'm just gonna add the oops. What did I do here? Okay, that's better. So that's the this is the same plot we had at the beginning, and now I'm gonna plot the arcs. So for each ij inactive arcs, we'll plot the x coordinate of j. And now it's gonna be y coordinate of y of j. And it needs to be lowercase there. That's better. Let's see, just gonna color them all the same color, green, for example. And the order is off, so you might wanna plot first the lines and then the dots. It didn't work. You can just have set order equal to 0 there. That's better. So those would be all of the routes. It doesn't look quite well here, but it's maybe just because of the data. Let's try another seed. So if I tried, so for example, seed number 4, for example, I'll restart the kernel and run all of the cells again. I can find the optimal solution and see, and we can see here that there are 2 routes as a result. We can also have more clients. So for example, with 20 clients, let's see what happens. No, this one here. All right, so this is interesting. So now it starts to take more time. If you're actually seeing this video, you already know that this problem is NP hard. So it's very, for computation, it's very expensive. And so when you're playing with small instances, it's easy to solve. But once you go like clearly now with only 20, it's taking a lot longer. But if you notice here, Gurobi already has an incumbent solution. It basically, and what's trying to do now is trying to prove optimality, and it's finding a very feasible solution, as well as improving the lower bound of the relaxation. So the idea here is to get these two numbers to the same point, to be equal. And then, the gap would be 0, and then we will have that the incumbent solution would be the optimal solution. Usually, we don't have this much time, and so we would want to interrupt this if it's reached a certain time or a gap. So I'm just gonna restart this and clear all of the outputs. And I'm gonna add a condition here, right here, before calling the optimizer. And I'm gonna set some parameters. So MIP gap. So whenever the solution is within a 10% gap, the optimizer will stop. Or instead, if a certain limit in time has been reached, then also it'll stop. It'll stop whenever the the one that first, the condition that first met, it will produce the optimizer to stop. Okay, so these are seconds, by the way. So I'm gonna run it again. So now it's all clear up. I'll run all the cells. And now I'm supposed to stop after 30 seconds. Let's see. So it already has 10 seconds. It has well, the gap is over 40. It's really far from 10%. So most likely it'll stop because of the time limit rather than the gap. There. So it stopped right after it reached 30 seconds. And here you can see time limit reached. Solution count, it found 10 solutions. The one that you're actually plotting here is the best one among those 10. And the gap ended up being 44. So this would be a feasible solution, not an optimal solution. All right, and that's how it looks. All right, thank you very much for seeing this video.